The one discovery that would change everything. If you woke up tomorrow and every alert on your phone said, alien life confirmed, what single piece of evidence would you need to actually believe it? Not just a headline, not a rumor. The one discovery that would make you stop, stare at the screen, and feel the ground shift under your feet, because that is what we are really talking about. Not a cool science story, a civilizational shock. In the hunt for alien life, a true confirmation would not just add a new chapter to astronomy, it would rewrite our place in the universe. Overnight, every religion, every philosophy, every story we tell about why we are here would have to respond to a new fact. Life did not begin and end with Earth. This means our long-term survival plans, from planetary defense to interstellar travel, suddenly become less abstract and far more urgent. And yet, look at what we already have. We have found more than 5,000 exoplanets, orbiting distant stars in every direction we look. Some sit in the Goldilocks zone, where liquid water could exist. We have detected oceans under the ice of Europa and Enceladus, with plumes that may carry complex chemistry into space. We have glimpsed strange molecules in alien atmospheres and spent decades listening for radio whispers from other civilizations. But while the majority of people believe alien life is out there, no scientist is willing to stand on a stage today and calmly say, yes, aliens exist, in the present tense. Why? What is still missing? It should be noted that science is not waiting for a blurry UFO video or a mysterious light in the sky. The real threshold is much sharper than that. There is a specific kind of pattern we are hunting for, a set of gases in a planet's atmosphere that cannot be explained by geology alone, or a narrow-band radio signal, or a precise infrared flash that carries the unmistakable fingerprint of technology. These are biosignatures and technosignatures, and multiple telescopes are already searching for them right now. JWST is dissecting the atmospheres of distant worlds, like K2-18b. Ground-based observatories are scanning nearby stars for artificial radio beacons. Future missions will be able to image Earth-like planets directly and look for oxygen, methane, and even possible pollution. So it's time to find out the truth. How close are we, really, to the one piece of evidence that no one can argue with? Not just, do aliens exist? But, what would undeniable proof actually look like? And which missions are most likely to see it first? So, let's begin. Why proving aliens exist is so hard. So if we are waiting for undeniable proof, what does that actually mean? In everyday life, one dramatic photo or a strange light in the sky might feel convincing. In science, it is almost the opposite. One blurry UFO image is where the conversation starts, not where it ends. In the hunt for alien life, proof really means a web of independent evidence that all points to the same conclusion and survives every alternative explanation we can throw at it. This means different instruments, different teams, and different methods all have to agree. If there is even one solid natural explanation left on the table, scientists will not declare victory. To get there, researchers usually talk about three main kinds of clues. First, biosignatures, chemical fingerprints in a planet's atmosphere or oceans that are hard to produce without biology. Second, technosignatures, signs of technology like narrow-band radio signals, laser flashes, or even unusual industrial pollutants. Third, statistical arguments, the big picture reasoning like the Drake equation that says the universe should be full of worlds and civilizations. It should be noted that each of these sounds simpler than it really is. Take biosignatures. Oxygen paired with methane in an atmosphere around an Earth-like planet is often called a smoking gun for life because those gases rapidly destroy each other and must be constantly replenished. But while that is true here, on another world, active volcanoes, exotic chemistry, or a strange ocean could mimic the same pattern without any cells at all. Technosignatures face the same problem. A sharp radio signal could be a distant civilization, or it could be a satellite in Earth orbit, a radar on the ground, or a natural flare from a star. Even an odd dimming of a star that looks like a megastructure can turn out to be dust. Optimistically speaking, our detectors are sensitive enough to be confused by many things, and the grand statistical arguments, they are powerful for framing the question, but they are not direct detection. The Drake equation can tell us that many habitable planets should exist in our galaxy, but it cannot tell us whether any specific system, any specific world, is actually alive. We saw this tension play out recently with K2-18b. Early James Webb data hinted at intriguing molecules in its atmosphere, possibly even dimethyl sulfide, a gas on Earth strongly associated with life in the oceans. Headlines leapt ahead to signs of life, but the signal was weak, right at the edge of what Webb can see, and fully compatible with non-biological chemistry. So the cautious verdict was interesting, but far from proof. So where does that leave us, now that Kepler, TESS, and JWST can actually sniff alien atmospheres and scan the sky for signals? Are we still in the dark, or already brushing against that evidential threshold without realizing it? Because the next step is to look at what these telescopes are really finding, and which specific planets might be first to cross the line, from are we alone to specific worlds and signals. To answer that, we have to notice how the question itself has changed. For most of human history, are we alone was a philosophical debate. Today, in the hunt for alien life, it has become an engineering problem. Which specific planet, which exact wavelength of light, which narrow band of radio frequencies do we stare at, and for how long? This means that instead of arguing in the abstract, we now draw up target lists. We know that Earth-like planets in a star's Goldilocks zone are our best starting point, because that is where liquid water can persist on the surface. So we look at systems like TRAPPIST-1, with 7 rocky worlds, packed close to a cool red dwarf, and ask, which of these orbits receive the right amount of energy, and which atmospheres can JWST actually dissect? But TRAPPIST-1 is not alone. Kepler and TESS have revealed thousands of planets, and some of them sit in that delicate habitable band. K2-18b, for example, is a sub-Neptune with hints of interesting chemistry in its atmosphere, while Proxima b orbits the closest star to the Sun, right in its Goldilocks zone. These are no longer distant ideas. They are coordinates in a telescope schedule, with follow-up observations already planned. Pattern interrupt for a second. Not all of our best bets are distant exoplanets. Some of the most promising places for life might be hiding right here in our own backyard. Europa and Enceladus are icy moons with global oceans beneath their crusts, venting plumes of water and organics into space. It should be noted that we can, in principle, fly through those plumes, sample them directly, and ask whether anything in that chemistry looks like biology rather than geology. So, let's begin to separate our search into 2 parallel quests. One is for simple life, microbes, biosignature gases like oxygen and methane in the same atmosphere, or any chemical disequilibrium that would be hard to maintain without something living and metabolizing. The other is for intelligence, radio SETI listening for narrowband signals, optical SETI watching for laser flashes, and hunts for technosignature such as waste heat, megastructures, or even industrial pollution. On paper, these approaches look very different. A spectrograph sniffing an exoplanet atmosphere and a radio dish scanning the sky do not seem related, but while the tools change, the goal does not. Each method is trying to find an alien fingerprint that nature, by itself, would struggle to fake, a molecule in the wrong ratio, a pattern in time that screams engineering, a glow of energy that does not match any normal star or planet. Optimistically speaking, we might already be close, so it's time to find out the truth. In the rest of this video, we will walk through these fronts one by one, starting with how we even define a convincing alien fingerprint, and then asking, at every step, how close the current data really are to crossing the line from interesting to undeniable. What would count as an alien smoking gun? So if we did stumble on proof, what would it actually look like? In the hunt for alien life, what is the one piece of evidence that would force us to say, this is not just a weird planet, this is biology or technology? Scientists have a name for the first category, biosignatures. It should be noted that a biosignature is not usually one magic molecule floating alone in an atmosphere. Instead, it is a pattern, a combination of gases, energy flows, and environmental context that, taken together, are extremely unlikely to arise without life. Think of it as a fingerprint, not a single fingerprint line. On an Earth-like world, the classic example is oxygen plus methane. Oxygen is so reactive that on a rocky planet it should quickly rust the surface or react away. Methane is also fragile. Ultraviolet light from a star destroys it, but while each gas on its own could be made by volcanoes or chemistry, keeping both in large sustained quantities means something is constantly replenishing them. This means some active process, very much like metabolism, is fighting the natural tendency toward chemical balance. We also look for strong chemical disequilibrium more generally. An atmosphere packed with oxygen next to reduced gases, or unexpected ratios of carbon dioxide, water vapor, and methane can all hint that the planet is out of simple geologic balance. On Earth, biology pushes our air far from what geology alone would do. Add in more exotic gases, like dimethyl sulfide, which on Earth is mainly produced by plankton in the oceans, and the case gets stronger. None of these molecules would be enough alone, but together, in the right Goldilocks zone, they begin to look like a living system. A useful way to picture this is to imagine walking into a room. You smell smoke, that could be from a candle. You see heat shimmer, that could be from a radiator. You hear crackling, that could be a speaker. But all three at once, smoke plus heat plus crackling, in the same place and time, overwhelmingly point to fire. A biosignature is exactly that kind of layered, converging evidence on a distant planet. Technosignatures push the idea one step further. Instead of just metabolism, we look for technology, narrow-band radio beacons that stand out sharply from natural noise, intense, regular laser pulses, industrial pollutants like CFCs in an exoplanet atmosphere that have no known large-scale natural source, or even excess mid-infrared waste heat, as if some vast structure were intercepting a star's light and re-radiating it. Optimistically speaking, any one of these, if bright and clear enough, could be our smoking gun. But while our telescopes become more sensitive, something paradoxical happens. We see more strange, borderline signals, more odd spectra, and unexplained dimmings, yet it becomes harder, not easier, to say this cannot be geology or chemistry alone. So let's begin applying this framework to real worlds and ask, which planets right now are closest to crossing that invisible line? Meet the telescopes that are hunting for life. To answer that, we need to meet the machines that are actually watching these worlds, because in the hunt for alien life, everything depends on what our telescopes can and cannot see. The first big leap was Kepler. This space telescope did something almost absurdly simple. It stared at one tiny patch of sky and waited. Every time a planet crossed in front of its star, the starlight dipped by a fraction of a percent. From those tiny flickers, Kepler revealed a shocking truth. Planets are everywhere. It should be noted that Kepler's data showed that Earth-sized planets in the Goldilocks zone are not rare exceptions, but statistically common. This means that when we talk about an Earth-like world around a distant star, we are not daydreaming, we are extrapolating from thousands of real detections. But while Kepler gave us statistics, it mostly looked at distant, faint stars, far too dim for us to study their atmospheres in detail. So let's begin the next phase. TESS, the Transiting Exoplanet Survey satellite, took Kepler's method and wrapped it around the whole sky. Instead of staring at one field, it tiles the celestial sphere, focusing on nearby, bright stars. Why does that matter? Because planets around these stars are close enough, and the stars are bright enough, that we can attempt follow-up observations, dissecting their atmospheres today, and even directly imaging some of them in the future. Optimistically speaking, TESS is building the shortlist of worlds where we might actually read the chemical fingerprints of life. Enter the current flagship, the James Webb Space Telescope. JWST is tuned to infrared light, the glow of heat, where molecules leave their signatures. When a planet transits, a thin ring of starlight filters through its atmosphere before reaching us. JWST spreads that light into a spectrum and looks for the telltale patterns of water vapor, methane, carbon dioxide, and other gases. On worlds like K218b and the TRAPPIST-1 planets, it is already measuring whether their atmospheres are thick or thin, steamy or stripped, potentially habitable or clearly hostile. But space is only half the story. On the ground, huge observatories in Chile and Hawaii are pushing the limits with advanced spectroscopy and adaptive optics, sharpening blurred starlight in real time. And on the horizon are the true giants: the extremely large telescope, the Giant Magellan Telescope, and the 30-meter telescope. These instruments aim to separate the faint glow of a planet from the glare of its star, then read its spectrum for possible biosignatures, all without ever leaving Earth. So it's time to find out the truth. For the first time in history, our telescopes are, in principle, capable of detecting life-related signals on distant planets. The tools are finally here. The obvious question is, with all this power, what are they actually seeing? And what are they not seeing? Two futures: silent cosmos or crowded sky. So right now, with JWST and all these new instruments finally online, we're being pushed toward a very stark choice. Either the universe starts talking back to us, or the silence becomes impossible to ignore. In the hunt for alien life, this is the real crossroads. As our telescopes sharpen and our detectors improve, there are only two broad futures left. Either we begin to see clear, repeatable signs of life in the data, or mission after mission comes back empty until the quiet itself becomes a kind of measurement, not just disappointing, but statistically deafening. What happens then? Let's imagine the first path. JWST, or a next-generation mission like the Extremely Large Telescope, or a future Life Finder space observatory, locks onto an Earth-like planet in the Goldilocks zone of a nearby star. We take spectrum after spectrum of its atmosphere. At first it looks ordinary, some CO2, some water vapor, but then the pattern refuses to fit any non-biological model. There is abundant oxygen, methane sitting alongside it, and subtle trace gases in ratios that, on a geologically quiet world, should destroy each other in a few thousand years. Yet they are there, stably replenished. This means something on that planet is constantly rebalancing the chemistry. Volcanoes alone cannot do it. Photochemistry cannot do it. We would be forced, cautiously at first, to say the word life. Now take the other path. It should be noted that so far, most of the atmospheres we've been able to probe look harsh. Barren rocks blasted by their stars, toxic skies thick with hydrogen or carbon monoxide, steam worlds with temperatures in the hundreds of degrees. Imagine that continues. Kepler, TESS, JWST, and the missions that follow survey thousands of promising Earth-sized planets in the right orbit around calm stars, and every single one turns out sterile. No biosignature gases, no weird chemical imbalances, just lifeless oceans and deserts where, on paper, life should have had every chance. At that point, the Fermi paradox stops being a philosophical puzzle and starts looking like a warning. Optimistically speaking, maybe life is rare but long-lived. Less optimistically, maybe it is common to start and very easy to extinguish. Either way, a long, well-documented null result would make Earth look less like a typical planet and more like a bizarre cosmic lottery winner. Our entire picture of how easily life arises would have to be rewritten. So let's begin to frame the rest of this episode around that tension. So it's time to find out the truth by looking at the actual clues we have right now. From strange molecules in exoplanet atmospheres, to hidden oceans on icy moons, to the faint possibility of artificial radio signals, we'll ask of each one, does this nudge us toward a crowded sky, or toward a profoundly, unsettlingly silent cosmos? Who's talking to you, and where we're going in this episode? So who is actually walking you through this cosmic detective story? I am Alex, and this is Deep Sky Signals, where we take the latest space science, strip away the hype, and then add just enough drama back in to show why it really matters. In the hunt for alien life, we have a simple rule on this channel. We follow the data, even when it leads somewhere uncomfortable. This episode is not just a tour of cool planets and mysterious stars. Our goal is to systematically narrow down how close we are to real, defensible evidence of life, using what telescopes like JWST, Kepler, and TESS have actually seen, and what the next generation of missions might reveal. This means we are going to treat aliens exist as a scientific claim, not a wish. So, let's begin by setting the rules of the game. First, we will pin down what would even count as proof. Is a weird molecule in an atmosphere enough? Do we need a repeating radio signal, or a picture of something swimming in an alien ocean? We will talk biosignatures, technosignatures, and why some headlines leap years ahead of what the measurements truly show. Then, we head out across the exoplanet front. We will visit the TRAPPIST-1 system, where 7 Earth-like worlds crowd close to a cool red dwarf, and ask which of them, if any, could actually be habitable. We will look at K218b, the so-called Hycean world that sparked claims of strange chemistry, and Proxima b, our nearest known potentially habitable neighbor. At each stop, we will ask the same question: does this move the needle toward life, or not yet? Pattern interrupt for your brain. If tomorrow JWST announced oxygen and methane together in one of these atmospheres, would that be it? Case closed? It should be noted that even that scenario has traps, and we will see why. After exoplanets, we dive inward to ocean worlds in our own solar system. Europa, with its salty global ocean under ice, Enceladus, spraying material from a hidden sea into space. We will look at what Cassini already found in those plumes, and what upcoming missions could directly test for life in those dark waters. From there, we will raise the stakes and talk about intelligence, radio SETI, optical SETI, and the search for technosignatures and even megastructures around distant stars. So it's time to find out the truth about what kind of signal would force almost every scientist on Earth to agree something out there is talking. Finally, we will look ahead at the telescopes that might tip the scales, giant ground-based observatories, NASA's Roman mission, and future concepts designed specifically to read the atmospheres of truly Earth-like planets in the Goldilocks zone. All along, we will flag what is rock solid, what is speculative, and where the universe is still refusing to answer. Optimistically speaking, by the end, you will be able to place your own marker on that spectrum from "we are nowhere" to "we are on the brink," and see why the real answer may be stranger and more exciting than either extreme. Exoplanet atmospheres, reading alien weather for life. So if we want to move along that spectrum toward "we are on the brink," where do we actually look? In the hunt for alien life, the most powerful place to start is not the surface of a distant planet, but its sky. When an exoplanet passes directly in front of its star, something subtle and extraordinary happens. For a few hours, a tiny fraction of the starlight does not go straight to our telescopes. It filters through the planet's atmosphere first. Different gases absorb different colors of light, leaving behind a barcode-like pattern in the spectrum. This method is called transit spectroscopy, and it lets us read alien weather from tens of light years away. We measure the star's light before, during, and after the transit. If, during the transit, certain colors are missing or dimmer, we know something in the atmosphere has blocked them. Water vapor leaves one pattern, methane another, carbon dioxide another. This means, from a single flickering dip in brightness, we can infer the invisible. Clouds, haze, temperature, even hints of chemistry that might support life. But while this sounds straightforward, it should be noted that star and planet each complicate the picture in their own ways. The type of star, its activity, and its brightness determine which worlds we can even study. A large, noisy star can drown out the delicate signal from a small planet. Meanwhile, the planet's size, temperature, and composition control what kind of atmosphere, if any, can exist, and how thick that spectral barcode will be. This is why small, cool stars called red dwarfs have become prime targets. Because they are dim, an Earth-like planet blocks a larger fraction of their light. Their Goldilocks zone is close in, so planets in the habitable region orbit quickly and transit often. More transits mean more data, and more data means clearer spectra. Optimistically speaking, these systems give us our best current shot at detecting biosignature gases, but while red dwarfs help us, they also fight us. Many flare violently, blasting their planets with ultraviolet and X-ray radiation. Over billions of years, that radiation can strip away atmospheres or drive exotic chemistry that mimics life. So, if we see oxygen or methane around a planet orbiting a young active star, is that biology, or just harsh starlight tearing molecules apart and rearranging them? Context becomes everything. The same gas mix can mean very different things in different systems. Oxygen around a hot, young star might be a photochemical artifact, produced as water is broken apart and hydrogen escapes. Yet oxygen around a quiet, older star, combined with methane and water in the right ratios, would be far more compelling. So it's time to find out the truth in real examples. In the next sections, we will watch these principles collide with actual data from TRAPPIST-1, K2-18b, and Proxima b, and see why, despite all this exquisite information, none of them yet count as universally accepted proof of life. TRAPPIST-1, and the promise and pain of many Earths. So if the rules on paper are that clear, where do we test them in the real universe? In the hunt for alien life, one star system has become the ultimate proving ground. TRAPPIST-1, just 7 letters and a number, but behind that label sits one of the most extraordinary planetary systems we have ever found. This tiny, ultra-cool red dwarf lies about 40 light-years away, only a bit larger than Jupiter in size, but far more massive, glowing dimly in infrared. Around it, 7 Earth-sized rocky planets circle in an elegant chain, at least 3 of them receiving just the right amount of starlight to sit in the Goldilocks zone, where liquid water could, in principle, exist. So, let's begin with how we even discovered such a compact clockwork of worlds. In 2015 and 2016, a pair of small Belgian telescopes called TRAPPIST stared at this faint red dwarf, using transit photometry to watch for tiny dips in brightness as planets crossed the star. First, the data revealed 3 Earth-like planets. That alone was remarkable. But follow-up observations with larger ground-based telescopes and then NASA's Spitzer Space Telescope kept adding dips, refining orbits, and untangling overlaps until the full 7-planet lineup snapped into focus. Why did that announcement electrify the field? Because for once, nature had given us almost everything we could reasonably ask for. Multiple rocky, Earth-sized planets, orbits so tight that years last days, meaning frequent transits and lots of chances to measure them. A small cool star, which makes the relative signal of each planet's atmosphere larger. This means TRAPPIST-1 is practically a custom-built laboratory for the James Webb Space Telescope to probe for water vapor, carbon dioxide, methane, and one day, maybe even biosignatures. Early JWST results, however, have been both encouraging and frustrating. It should be noted that Webb has already shown that at least some of the inner planets, especially TRAPPIST-1b and 1c, almost certainly lack thick, puffy, hydrogen-rich atmospheres. They are not mini Neptunes. That is good news if you care about solid, potentially habitable surfaces. But the flip side is brutal. Without those big, extended atmospheres, the spectral fingerprints we are looking for become incredibly faint. Optimistically speaking, that means these worlds might be truly rocky, with compact atmospheres more like Earth or Venus. Realistically, it also means that even for this dream system, JWST is straining at the edge of what is possible. So far, we do not have a single, unambiguous atmospheric detection for a clearly habitable TRAPPIST-1 planet, let alone a convincing biosignature. So it's time to find out the truth about just how far we can push Webb here and which of these 7 worlds still stand a chance. Because if TRAPPIST-1 is this hard, what does that mean for every other target on our list? K218b, Proxima b, and the temptation of early hype. If TRAPPIST-1, our best nearby laboratory of small worlds, is this hard to read, what hope do we have with stranger, more distant planets? In the hunt for alien life, this is where the story of early hype really begins. So, let's begin with K218b. On paper, it sounds almost made to generate headlines. It orbits a red dwarf star, about 124 light-years away, right in the Goldilocks zone, and it is larger than Earth, but smaller than Neptune. Astronomers call it a mini-Neptune, and some have proposed a new class for it, a Haitian world, with a global ocean hidden beneath thick, hydrogen-rich clouds, a dark, warm sea under a permanent twilight sky. How could we not be tempted by that? When JWST turned its mirrors toward this system, the data did something dramatic. In the planet's atmosphere, we see clear signs of water vapor, methane, and carbon dioxide. This means K218b is not a simple, dead ice ball. It has an active, layered atmosphere, and the mix of gases hints at complex chemistry, maybe even conditions where liquid water could exist at depth. Optimistically speaking, that sounds like an environment where some form of life might be possible. But then came the real spark, a tentative hint of dimethyl sulfide, or DMS. On Earth, almost all DMS in the atmosphere is produced by marine life, especially tiny plankton in the oceans. So if you hear DMS on an exoplanet, your brain immediately jumps to alien biology. However, it should be noted that this particular signal is right at the edge of what JWST can see. The detection depends heavily on which models you use to fit the spectra. The signal to noise is low, and we do not actually know whether non-biological processes could make DMS on a Haitian world. Most scientists treat it as a curious whisper, not a discovery. Proxima b shows the other side of this problem. It is the closest potentially habitable exoplanet we know, orbiting Proxima Centauri just over 4 light-years away. The planet has a minimum mass similar to Earth and sits in the star's habitable zone. That sounds ideal. But while the orbit looks friendly, the star itself is violent. Proxima Centauri is a flaring red dwarf, blasting out frequent bursts of high-energy radiation that can strip atmospheres and sterilize surfaces. Does Proxima b have a thick atmosphere that survived, or is it an airless, irradiated rock? Right now, we simply do not know. Together, K218b and Proxima b reveal a new gray zone. Our instruments are finally good enough to see water, methane, and possible atmospheric disequilibria, yet every signal is just ambiguous enough that the community refuses to declare victory. So it's time to find out the truth about our limits here. Are we just one more telescope away from clarity? For exoplanets, we are probably one or two major generations away from routinely mapping detailed atmospheric chemistry and seeing multiple, cross-checked biosignatures at once. Which raises a provocative question. If distant planets are still so uncertain, could our first solid evidence for life actually come from much closer to home, inside our own solar system instead, Europa, Enceladus, and the oceans beneath the ice? If our first proof of aliens does not come from a distant exoplanet, could it rise out of an ocean we cannot even see? In the hunt for alien life, two of the most intriguing oceans are not on any planet at all, but inside icy moons, Europa and Enceladus. Both worlds look frozen and dead from the outside, but while their surfaces are locked in ice, their interiors tell a different story. These moons are constantly flexed by the gravity of their parent giants, Jupiter and Saturn. That tidal squeezing generates heat, and this means vast global oceans can stay liquid beneath tens of kilometers of ice, protected from radiation and stable for billions of years. On Earth, long-lived water plus energy is exactly where life thrives. Enceladus gave us the first real taste of this hidden potential. When the Cassini spacecraft flew past, it saw towering plumes of water, vapor, and ice grains jetting from cracks near the South Pole. Scientists flew Cassini straight through those plumes. The data revealed salts, simple organic molecules, and tiny silica grains that strongly suggest hot water reacting with rock on the seafloor. In other words, hydrothermal vents. On our own ocean floor, similar vents host dense ecosystems that do not depend on sunlight at all. So, let's begin to see Enceladus not as a passive ice ball, but as an active, energy-rich ocean world. Europa, orbiting Jupiter, offers a different but equally compelling case. Its surface is crisscrossed with ridges and chaotic jumbled ice, as if slabs have broken, rotated, and refrozen. That kind of geology hints that the ice shell is floating on a mobile, possibly salty ocean. Even more persuasive, Europa moves through Jupiter's powerful magnetic field in a way that induces its own magnetic signature, best explained by a global, electrically conducting ocean. It should be noted that Hubble has even seen hints of possible plumes, suggesting that deep water might occasionally vent into space, just as on Enceladus. This is where upcoming missions become critical. NASA's Europa Clipper and ESA's JWST spacecraft will both explore the Jovian system in the 2030s. They will map Europa's ice thickness, probe the ocean's depth and salinity, and measure surface chemistry in exquisite detail. If plumes are active, they may fly directly through them, sampling for complex organics, unusual energy gradients, and perhaps even patterns in the molecules that look more like metabolism than random chemistry. Optimistically speaking, that is the kind of multi-layered evidence exoplanet telescopes can only dream about. The key advantage here is proximity. Unlike distant worlds in the Goldilocks zone of some red dwarf star, we can send instruments straight into the environment. We can taste the water, weigh the particles, and look for cell-like structures under a microscope. But even then, what if we only find ambiguous chemistry, rich in organics yet lacking clear biological patterns? Would that be enough to say, yes, aliens exist? Or would we still be trapped in doubt? So, it's time to find out the truth. If hidden oceans might hold microbes, could something far more dramatic announce itself across interstellar space instead? Listening for minds, radio SETI, lasers, and megastructures. If microbes might whisper from an icy moon, could a civilization shout across the galaxy? In the hunt for alien life, this is where we stop looking for chemistry and start listening for minds. For more than half a century, Radio SETI has been our main ear on the universe. Giant dishes like Arecibo and Green Bank have swept the sky, searching for extremely narrow-band radio tones that nature almost never makes. Among the static of stars, pulsars, and distant galaxies, we look for a signal that is too clean, too precise, too artificial to ignore. In 1977, one such signal appeared, a strong, tidy spike from the constellation Sagittarius. The astronomer who saw the printout simply wrote, "Wow," in the margin. But while the wow signal was dramatic, it never repeated. This means we cannot test it, cannot decode it, and cannot prove it was a message rather than a strange, one-off glitch. Modern SETI has evolved into something far more ambitious. Arrays like the Allen Telescope Array and piggyback projects on huge observatories now record billions of radio channels at once across wide swaths of sky. Software combs through the data, searching for drifting tones that would match a planet's orbit or the spin of a distant star. We have scanned nearby sun-like systems, regions toward the galactic center, even the plane of the Milky Way, where civilizations might be most common. Yet, despite terabytes upon terabytes of listening, no repeating, verified beacon has emerged. So, let's begin a different kind of search. Instead of radio, what if advanced civilizations use light itself? Optical SETI looks for ultra-short laser flashes, pulses lasting billionths of a second, that outshine their host star for an instant. It should be noted that our detectors have recently become sensitive enough to catch these brief bursts over interstellar distances. Telescopes now stare at nearby Earth-like worlds, and at dense clusters of stars, waiting for a single, unnatural blink. Pattern interrupt. Not all technosignatures need to be messages. What if the easiest thing to detect is not a greeting, but pollution or waste heat? Astronomers are beginning to search exoplanet atmospheres for industrial chemicals such as CFCs, molecules that do not occur in large amounts without technology. Others are scanning the sky in mid-infrared light, hunting for stars that seem oddly dim in visible light, yet wrapped in a glow of warm dust. Optimistically speaking, that excess heat could betray vast megastructures, Dyson sphere-like swarms, harvesting a star's energy. So it's time to find out the truth. How close does this bring us to proof? Even after decades, the region of signal space we have searched is a tiny fraction of what is possible. Different frequencies, timescales, and sky locations remain almost untouched. This means the silence so far is not decisive, until we see a signal that repeats, carries structure, and clearly cannot be natural, or we catch some new technosignature in upcoming data. We are still listening, still waiting. And if the universe stays quiet, then we have to ask a much darker question. What if the civilizations themselves are the missing piece? The next wave of LifeFinder missions. If civilizations might be the missing piece, then the next question is obvious. Can we build machines powerful enough to find life before it finds us? In the hunt for alien life, the next few telescopes are not just upgrades. They are a complete change in how we look at the universe. So, let's begin with the one that is already on the way. NASA's Nancy Grace Roman Space Telescope. Roman will carry a technology demonstrator called a coronagraph, a kind of super precise light blocker that can cancel out the glare of a nearby star. This means, for the first time, we will directly image some exoplanets not as shadows passing in front of their stars, but as faint points of reflected light beside them. From that light, we can take spectra and search for signatures of clouds, hazes, and broad atmospheric features, even when the planet does not transit at all. Why is that so important? Because transits only work for a tiny fraction of planetary systems, perfectly lined up with our line of sight. Direct imaging opens up many more nearby stars, including some of the best candidates for habitable, Earth-like worlds. It should be noted that Roman's coronagraph is still a test bed, not a full life finder, but if it works, it proves that this way of seeing planets is ready for something bigger. On the ground, bigger is almost an understatement. The extremely large telescope in Chile, the giant Magellan Telescope, and the 30-meter telescope are all designed around enormous mirrors and advanced adaptive optics, systems that constantly reshape their mirrors to cancel out Earth's turbulent atmosphere. But while their primary job is to collect light, their real power is in what that light can tell us. With high-resolution spectroscopy, they should be able to tease out combinations of gases in the atmospheres of the closest rocky planets, oxygen with methane, or carbon dioxide with water vapor, patterns that might hint at biological activity. Then, there are the truly ambitious concepts, LUVOIR and HABEX. These proposed space observatories would be built from the start as life hunter machines, with huge mirrors, ultra-stable optics, and either internal coronagraphs or separate star shades flying alongside. Their explicit goal would be to directly image Earth-like planets in the Goldilocks zones of sun-like stars and measure their atmospheric compositions in exquisite detail. Optimistically speaking, a single unambiguous spectrum from such a world could change every biology textbook on Earth. Not all promising habitats are distant exoplanets. Closer to home, mission concepts target the ocean worlds of our own system, Europa and Enceladus. Future landers or plume-sampling orbiters could fly through icy jets, tasting the spray for complex organic molecules, unusual isotopic ratios, and even cell-like structures. Instead of a faint spectral line across light years, we would be holding alien chemistry in our instruments. Taken together, these telescopes and probes are the cosmic equivalent of turning up the volume and sharpening the focus on everything around us. So it's time to find out the truth. With this hardware, are we finally within one human lifetime of a consensus-level detection of life, or will the silence only grow louder in the next data? So, how close are we, really? How close are we, really, to proving that aliens exist? We have all this new hardware staring at distant worlds and icy moons, but where does that actually leave us in the hunt for alien life right now? On one front, we have exoplanet atmospheres. JWST is already dissecting the light from planets like TRAPPIST-1e and K2-18b, looking for combinations of gases that should not sit together in a dead atmosphere. Future giants like the Extremely Large Telescope and NASA's Roman Space Telescope will push this even further, resolving smaller, cooler, more Earth-like planets in the Goldilocks zone of their stars. At the same time, closer to home, Europa Clipper and JWST are heading for the subsurface oceans of Europa and Ganymede, while proposed missions to Enceladus could fly directly through plumes and taste them for organic chemistry. And above all of this, radio and optical SETI projects are still listening, scanning the sky for technosignatures from any distant system that might already be broadcasting. This means we are no longer in the era of pure speculation, where we just plug numbers into the Drake equation and argued. We are in what you could call the pre-decisive data era. We finally have instruments that can see hints, borderline cases, atmospheres with odd chemistry, methane spikes on Mars, strange radio bursts that almost look artificial, but not yet the routine, high-signal observations that would make a claim of life essentially bulletproof. One clear spectrum, one repeating technosignature could change everything, but right now each candidate still comes with a long list of non-biological explanations. So what about timelines? Optimistically speaking, the next few decades are where the probability really starts to rise. As JWST, Roman, and ELT-class telescopes build up a library of exoplanet spectra, the odds increase that one atmosphere will stand out as deeply, stubbornly hard to explain without biology. As Europa Clipper maps ice shells and measures chemistry, and any future lander or plume sampler returns data, we could find clear energy sources and complex organics in those dark oceans. Add in continuous technosignature searches across radio, optical, and infrared wavelengths, and it becomes less and less likely that an active broadcasting civilization nearby would escape notice forever. It should be noted that the universe does not owe us an easy answer. Life could be common, but mostly microbial, hiding beneath ice or rock where its signatures barely leak out. It could be rare, but spectacularly obvious when it finally appears, lighting up an atmosphere with oxygen and methane. Or it could be based on chemistries and solvents we have barely considered, making our current biosignature checklists incomplete. So, let's begin to calibrate our expectations. We are probably not one press conference away today, but we may be one or two major missions away from the first evidence that, while still debated, seriously tilts the odds toward life on at least one other planet or moon. And if we look across the next century, with generations of telescopes and probes surveying thousands of worlds, it would actually be surprising if we learned nothing definitive either way. But if that first hint arrives, what would it look like? And how would we even recognize it as the moment everything changes? Your lifetime, our cosmic neighborhood. In the hunt for alien life, that moment would not arrive as a single blinding headline. It would arrive as a graph, a spectrum, a strange pattern in the noise that refuses to go away. So let's begin our final step back. We started by asking what proof would even mean. Not a blurry light in the sky, but a clear, repeatable signal in the data, a mix of gases in an exoplanet atmosphere that only biology seems able to maintain, a plume from an icy moon like Europa or Enceladus, carrying complex organics, or a deliberate radio pulse, a technosignature, cutting through the silence of space. From there, we crossed whole star systems. We looked at red dwarf worlds, such as TRAPPIST-1 and K2-18b, where planets huddle close in their Goldilocks zones. We saw how JWST can split their starlight into rainbows and read the fingerprints of molecules. We visited the dark oceans under ice, and we listened with SETI to skies that, so far, have remained quiet. This means we now know where to look, what to look for, and which instruments might finally tip the scales. Here is the part that should be noted that it is easy to miss. For almost all of human history, the answer to, do we have direct evidence of life elsewhere, was a simple no. No cave painter, no early astronomer, not even the first astronauts had any realistic hope of seeing that change. But while the past was empty of data, your lifetime will not be. We are, right now, building telescopes that can read the atmospheres of Earth-like planets and probes that can taste alien oceans. Optimistically speaking, people alive today may genuinely watch the transition from "we have no direct evidence" to "we have at least one solid, widely accepted detection." And whichever way the universe answers, everything shifts. If we find that life is common, that many planets and moons are habitable and actually inhabited, then Earth becomes one story in a vast living system. Our responsibilities change. We are no longer just protecting a rare oasis, but learning how to meet our cosmic neighbors. But if the skies remain eerily quiet, if world after world looks sterile, then this tiny blue planet becomes unimaginably precious. We might be the only thinking beings for light years, perhaps far beyond. So it's time to find out the truth, and to stay with the story as it unfolds. If you want to follow each step, from TRAPPIST-1 and K218b to Europa's hidden sea, subscribe and explore the deep dives linked here. Tell us in the comments what kind of discovery would convince you that aliens exist. A strange gas on a distant world? Microbes in an ice plume? A clear, structured radio signal? Somewhere, right now, photons and radio waves are already on their way, carrying the answer. All that remains is for us to build the right instruments, ask the right questions, and be ready for whatever the universe tells us.